Yeah, I have the wrong file. It's basically okay. You covered one like you like that's interesting.
All right. So continuing on from where we left off in the last lecture, we're going to talk about further considerations in diffraction, and then hopefully I can introduce at least one of these topics in Fraunhofer diffraction today. And just to remind you, in the last class we covered the general considerations for diffraction. We introduced the usual principle that we will be using to derive the diffraction patterns from various types of slits and apertures. And so that is the Huygens-Fresnel principle. And we saw that whenever the wavelength is sort of greater than or comparable to the size of the slit, that's when you're going to see diffraction, substantial amount of diffraction. And then we also discussed various regimes for Fresnel and Fraunhofer diffraction. I'm not going to repeat those, but generally you can think of Fresnel diffraction as being close to like a geometrical optics plus some fringes. And Fraunhofer diffraction is just more a pattern that appears once you are in the far field and then stays the same. It looks very different from the slit or the aperture itself, but then it just spreads out in angle basically and just remains the same pattern, just spreads out as we go further and further out into the far field. And we also saw an important condition, which is that the Fraunhofer diffraction regime will be correct whenever the incoming waves and the outgoing waves can be approximated as planar. Okay, so normally you would say that the waves are spherical coming out of the screen, out of the aperture, but now whenever we can approximate that as planar in the region where we're looking, where, for example, when we're far away from the slit, then we're going to be able to call that as Fraunhofer diffraction, and we derive the condition for the distance to the screen, which has to be greater than b squared over lambda for Fraunhofer diffraction. And furthermore, I showed you in the lab that it's possible to set up Fraunhofer condition in any kind of imaging sort of setup where we put our source here and our lens here. We put the source effectively at by putting it at a focal length away from this lens, we create planar wavefronts. And then you could imagine that if in the absence of this slit, what you would get is an image of the source back onto this point over here, right? Because we have plane waves coming in, we put the screen at a focal length away from L2, that means we will get an image of the source S over here on the screen. But in addition to that, what we actually observe is the diffraction pattern from the aperture, because what we are imaging is the plane waves that are being emitted from the aperture into the screen, and those are being focused at the screen. So effectively, the screen is also at infinity, the source is at infinity. So we have effectively created the Fraunhofer condition for diffraction. And usually the geometrical image will not be seen of the source because it will be too faint, because usually the apertures are kind of tiny coming from these. Okay, so we've talked about the Huygens-Fresnel principle. We said that we are taking a plane wave and we are coming in at some scatterers, which are the points along the wavefront, and those points emit spherical waves, or in the Fraunhofer condition, they basically emit planar waves. That's what we want to look at. And then the question is, how do you add up the superposition of these sources? So, of course, it's an infinite set of sources, right? Because any wavefront can be decomposed into n sources, but the n is basically infinity. But to understand the problem first, what we'll do is we'll look at n sources, finite number of sources n, okay? And the basic idea is simple. As I've already said, in the Fraunhofer, we have a plane wave coming in. So all of these sources are emitting in phase because they are on the same planar wavefront. And then we are looking in the far field. So these are also emitting plane waves in the far field. And which is kind of shown here. You get spherical waves, but effectively in the far field, they basically look like plane waves. And so now we want to calculate what is the sum of the waves from each of these sources, n sources in this case, and we are assuming that there is some finite separation d between the sources. Okay. The idea is very similar to this two slit or two source case that we did in Young's double slit. If I ignore all these sources, then I have two such sources over here. And you can see that the path difference between this source and this source is in this little region over here. And you could imagine, for example, if I were able to fit half a wavelength in there, that would be destructive interference between the two waves, because half a wavelength corresponds to a phase shift of pi. And therefore you get destructive interference. Then if you go down one more, now there is again a phase shift of pi between this and this one, or equivalently 2 pi phase shift between the first and the third one, and so on. Okay, and so this is how you can get constructive and destructive interference, and we want to sum up all of this. So obviously the total phase difference between the top and the bottom will be n minus 1 d sine theta, right? Remember, between any two sources which are separated by a distance d, we already saw this path length from the Young's double slit. This amount over here, this little extra length, is just d sine theta. Okay, so the next one will be from the top to the next one, which is r3 minus r1, just representing the distance r3 minus the distance r1 is 2d sine theta, 3d sine theta, etc., and then n minus 1 d sine theta at the bottom. Any questions about how I wrote that down? Oh, good. So if that is true, then what we have to do is add up all of these oscillators, add up all of the waves from each of these oscillators. We're going to assume that the electric field from each of those sources is some E naught as a function of R, but effectively this is going to be a constant. In the far field, this is just a plane wave. So it's a constant, and then the phase is e to the I k r1 minus omega t, e to the I k r2 minus omega t, etc., etc. And of course, we're assuming, as I've already said, they're illuminated by a plane wavefront, so it's the same phase on all of them. Okay. So then it's fairly obvious, hopefully, that we can just take out the e to the minus I omega t and the e to the I k r1 from each of these, and we'll be left with this exact thing that I just talked about, 1 plus e to the I k r2 minus r1, e to the I k r3 minus r1, etc. And I can just write that as delta. So I guess that I forgot the n minus 1, I put that as n. So basically, this r2 minus r1 is delta. K times r2 minus r1 is delta. Okay, r2 minus r1, of course, is d sine theta. I multiply that by k to get the phase difference. We talked about this in the last class as well. Okay, and then this 2 delta n minus 1.
Yeah, so sorry, did we do the Fourier transform of the waves here?
We did. We talked about the phasor representation of waves. Yes, at an earlier class.
So,
yeah, that's what we have written. The phasor representation. Okay, where delta now, which is the phase difference, I already said, is k times d sine theta. So that's 2 pi over lambda d sine theta. Okay, and now this is just a geometric series. So this 1 plus I e to the I delta, e to the I2 delta, e to the I n minus 1 delta, which I can just sum using the geometric series formula. Fairly simple to derive. If anyone wants to, I can go over that. But basically, the idea is you call this sum as S, right? Is equal to 1 plus all of that terms. And then I multiply by e to the I delta times S. And I'll get then the same series, except with all these terms essentially shifted over by 1. Okay. And then I just subtract one from the other. And then everything except the last term will cancel out. And then the first term also will remain constant. So those two terms will be left over here. And then you'll get this formula. It's a fairly simple calculation, as I'm sure you've all seen before. I'm just reminding you. Okay, from that, I can go to this expression. Okay. In case you're not sure how you do that, let me show you. This is a common trick. It's useful to see it once. So I have e to the I n delta minus 1 divided by e to the I delta minus 1. Okay. So what I do is in the numerator, I take out e to the I n delta over 2. I'm left with e to the I n delta over 2 minus e to the minus I n delta over 2. And in the denominator, I do the same thing. e to the I delta over 2 times e to the I delta over 2 minus e to the minus I delta over 2. Right? Everybody sees that because e to the I delta over 2 times e to the minus I delta over 2 is e to the 0 and e to the 0 is 1. Okay. All right. And now we use the formula that e to the I theta plus e to the minus I theta is 2 cosine theta. This is just taken by taking the Euler formula, or e to the I theta minus e to the minus I theta for any theta is 2I sine theta. Okay. And therefore, this numerator is 2I sine n delta over 2. The denominator is 2I sine delta over 2. And of course, I shouldn't forget the phase factors. So just recall, the phase factor is just e to the I n delta over 2 divided by e to the I delta over 2. So that's e to the I n minus 1 delta over 2. That's just a phase factor. And the part that is going to matter for the irradiance, remember irradiance is, this is the electric field. To find the irradiance, I had to square this. So all that really matters for the irradiance, and of course, 2 i's cancel out here. The part that's going to matter for the irradiance, the intensity, is the sine n delta over 2 by sine delta over 2 for expression. This. Yeah, that's just this formula over here, like I just derived. And now we can write everything back. We can put all of that back into the original field. Again, this is not super important for the irradiance, but it's helpful to look at that expression and see if it makes physical sense. So one of the things we can easily see is that the distance from the midpoint to the point P is just R1, which is from that first point, which was at the top, plus n minus 1 d over 2, because that's half the distance down to the bottom of the array. So the full distance to the bottom of the array was n minus 1 d sine theta. So then just divide that by 2, that'll be to the midpoint of this array. So that's the distance to the P point from the midpoint of the array. So we can write all of that effectively as e to the I k r minus omega t times this expression over here. Okay. So it's kind of more physical now. What all of these phase factors are representing is that there is a wave from the center of the array multiplied by some pattern which represents this sum of the phasors along each of the points. Okay. And so as I already mentioned, all of this can be written in terms of intensity as just I naught. So even the phase factor doesn't matter when I take intensity. It's just a norm squared, and therefore this is just sine squared n delta over 2 by sine squared delta over 2. So this is a very important sort of expression because as we'll see, this controls a lot of different things about the intensity and the resolution and so on of this pattern. Okay, and we can verify for n equal to 2. If I substitute n equal to 2 here, then I'm just going to get sine squared delta divided by sine squared delta over 2. Expand sine squared delta is 2 sine squared delta cosine squared delta over 2, and you'll get that this is just cosine squared delta over 2, which is of course the expression for the Young's double slit pattern that we've seen before. Okay, so at least we verified for the two slit or two source. I'll say slit and source equivalently because a slit is just effectively like a point source in the plane that is perpendicular to the orientation of the slit. Okay, so this is the n slit intensity distribution. So now let's look at some of its properties. So it's helpful when we see some new, always as physicists, mathematicians, whatever, you see some function like this, you're like, okay, well, of course I can go to Mathematica and I can plot it, right? Or Python or whatever and plot it. But it's also helpful to understand some limiting cases and understand the behavior of this expression. Yes.
Yeah, so I think I doubt that this equation can be obtained by just the dimensional analysis.
Good question.
Well, this is what I doubt. So
yeah, I don't know that we could have got it in dimension.
From the density of photons that is received, and then from
I agree. This definitely depends on the phase, so it requires some understanding of the analysis of the phase pattern from the slits. Right? Okay, so hopefully you can see the sine squared n, where if n were very large, this part would be fast varying, right? Because it's a sine function, but it's got an n factor in it. So as n becomes larger, it's just going to vary much more rapidly compared to the sine squared delta over 2. Okay, so that is slowly varying. So what we can argue is that the numerator and the denominator basically will go to 0 only when the delta over 2 is equal to m phi. And that's clearly, you can see that because sine squared n times m pi, right, is 0, and sine squared m pi over 2, or when delta over 2 is m pi, is also 0. Okay, so this numerator and denominator are basically going to go to 0. And so at that point is when we'll get a maximum. Okay, because you can obviously also see that if I were to take just the point where, say, n delta over 2 is equal to, let's say, equal to well, let's set that equal to, let's say, I'm going to put some random number, pi over 3 or something like that. Well, then when n delta over 2 is pi over 3, well, delta over 2 is pi over 3n. So for n equal to 10, so this delta over 2 is basically going to be much smaller. So this is almost going to be effectively just sine squared of 0, right? For some small value. Okay. Whereas the numerator might have some finite value. Okay. So we want to understand the situations where both of them go to 0, because that's where, of course, the numerator divided by the denominator becomes indeterminate. And we have to use some way of figuring out what that value of this function is. Okay. Well, okay, that's just some math. You've probably seen this maybe a long time ago in calculus. I just sketched it out over here, which is I use L'Hopital's rule. Okay. So L'Hopital's rule is I take the limit of, say, x going to 0 of sine squared nx by sine squared x. Okay. I wrote it for x equal to 0, but you can immediately see it's the same for delta over 2 equal to m pi, because the argument is the same whether delta is 0 or delta equals some 2m pi. It's the same argument here, because in both cases, the numerator and the denominator will both go to 0. Okay. So I chose x going to 0 because it's just simple to evaluate. So limit x going to 0, then by L'Hopital's rule, I differentiate the numerator and the denominator. Differentiate the numerator, I get that. Differentiate the denominator, I get that. And now I can just set both of these with x going to 0. I will get this function over here, n squared cosine nx divided by cosine x, and therefore I get n squared. So we see that as this function is basically going to this value delta over 2 equal to m pi, I'm going to get that the intensity now goes as n squared times I naught. This is very important. So for two slit pattern, we saw that the intensity was 4 times I naught at the maximum. Okay. So this is where we're getting maxima here as well. We're getting maxima when delta over 2 equals m pi or delta equals 2 m pi. Similarly, in the two slit case, we got when the delta, the phase difference was like 2 m pi or a sine theta was m lambda, we got a maxima. And that time the intensity went 4 times the intensity from one slit. So and now we have n slits, which is going to go as n squared. Okay, so it's a big, huge interference pattern. So again, I'm just writing this out. So when delta equals 2 m pi is when I get a maxima. So that is equivalent to 2 pi d sine theta over lambda equals 2 m pi, right? And therefore I get d sine theta equals m lambda. So this is the exact same condition as in the Young's double slit, d sine theta equals m lambda or sine theta equals m lambda over d. We'll see this sort of dependence of lambda over d. This is like something that's going to show up in a lot of diffraction and interference phenomena. Just remember that the angle is usually controlled by lambda divided by some size of something important in the problem. In this case, the size is just the spacing between the oscillators. Okay, so yeah, so at this point, so say here. Yeah, okay. And So this is the maxima, delta equals 2m pi. I just showed you that on the previous slide. And now I want to do this for, like, say 6. Okay, so if I have 6 slits, then I'm going to take the phasor from each slit and I'm going to add it up. Okay, and just to show you why this factor of 36 or n squared comes about. So if each phasor from each source can be written down, which is over here, this is the first phasor from the first point, the first oscillator in that array of oscillators. The next one, as we said, the phase difference between the first and the next one is delta. Okay, and that is 2m pi, let's say 2 pi in this case. So that's just a rotation of 2 pi, and then I put that second phasor over here. The next one rotates by 2 pi again. That also is going to be this one. Then rotate by 2 pi and place it next to that one. Add them all up, you get E equals 6 times E naught. So the total phasor, the total electric field is just 6 times the electric field from any one slit or any one source. And well, when I square that, I'm going to get 36 times the intensity from any one slit, which is that n squared I naught that I showed you also comes about from the function sine squared n delta over 2 by sine squared delta over 2. So this is just a visual representation of why we get a maximum when delta equals 2m pi. So if you, even if you don't remember the entire derivation on the previous slide, then at least from this visual representation, you can hopefully understand why delta has to be 2m pi to give you a maximum. Okay, so the first source and then the second source, they all add up constructively, meaning the phasors all line up together because of each one rotates by 2 pi with respect to the other one, or multiple of 2 pi. So when will be the minimum? Well, as you can imagine, if I add a phase shift of pi to each adjacent one, then each one will subtract from the other. So instead of 2m pi, if I have 2m prime pi plus 1 pi, just adding in a pi phase shift in between the slits, now each one, instead of going, it'll go 2 pi, and then I'll add an additional pi, so it'll be pointing opposite. So the first one, the second one cancel, then the next one and that one cancel, then the next one and that one cancel. So for 6, you get E equal to 0. So you see, we get destructive interference or minima when delta equals 2m prime plus 1 times pi. Okay. And you can also go back to this guy over here, and you can set when is this equal to 0? Well, obviously when the numerator goes to 0, but the denominator does not go to 0. And so you can set sine squared n delta over 2 equal to 0, and that will give you the same formula, 2m prime plus 1 pi as the formula for delta, because as I said, this sine squared function is slowly varying. So even when this n delta over 2 is some, is setting equal to 2m prime plus 1 pi, the denominator doesn't necessarily go to 0. Okay. But there are also other minima. So it doesn't just stop with this obvious minima. There are secondary minima, and they can be formed by not rotating this phasor by the entire pi back here, but by some intermediate angle such that the overall sum of this circles back and comes back to 0. So what do I mean by that? So imagine I did this m prime 2 pi over 6. 2 pi over 6 is just 60 degrees, basically. So for m prime equal to 1. Okay. So now you see the first phasor is down here. The next phasor rotates by 60, the next by 60, the next by 60, etc. And they close and form a closed form or a closed polygon in this phasor plane. And so now you can see again the total field, the sum of all of these phasors is 0, even though the angle isn't explicitly 2m prime plus 1 pi, but it is some angle 2m prime pi divided by 6. And again, as I said, because this is slowly varying, the denominator will not go to 0, right? Because 2m, so let's say it's 2 pi over 6 over here, that's just pi over 6, that's not 0, but the numerator will go to 0 because the sine squared of that 6 times 2 pi over 6 is going to be 2 pi, so that's going to go to 0. Okay, so again, both from the phasor picture as well as from the function itself, we can find the secondary minima over here. Oops, sorry. Okay. This is what I want to do. So this is the picture of the function that we have just seen. Okay, that I just derived. So here it's 36. That's because there were 6 slits and we added them up, or 6 sources. And so at each of these peaks, I get a 36 times the intensity of any one peak over here of any one source. And then it'll occur, as I just showed you, when delta is equal to 2 m pi. This is plotted as a function of delta over 2. So this first minima occurs as delta over 2 equals pi. Okay. No, sorry, maximum. Sorry. So that's what we call a principal maxima. Principal because it's so much stronger. It's 36 times the intensity, the square, n squared, times the intensity of any one source. So those are the principal maxima, really bright, spots. We already derived the minima. Those are here, these minima over here, and those are 2m prime pi divided by n. Okay, so those are over here, and then we have secondary maxima, which are in between the minimum. Okay? And roughly, we just take them as roughly halfway in between. You can, of course, calculate where they are explicitly by solving the transcendental equations. Sorry, that should have shown up as secondary maxima, but it didn't. But somehow blocked. But anyway, so those are the secondary maxima. And we saw, as I'm just saying, we saw that the minima will occur when n delta equals 2m prime pi. And by this argument that you want to form a closed hexagon or whatever other pattern, if you have 8 phases, it will be a closed octagon, etc. And you will get back that form that goes to 0. So the secondary maxima is in between 2 such values. Okay, so it's in between a value where n delta equals 2m prime pi and 2m prime pi plus 1, or 2m prime plus 1 pi, and it's such that the numerator is 1, but the denominator is slowly varying, so it doesn't go to 0. Okay, so that's going to give me 2m prime plus 1 pi over n. This is the position of all the secondary maxima. Okay, so this is very important. Just notice this because this is a common problem that you'll get in homeworks and tests and so on. Okay, so the secondary maxima is in between 2 of these minima, and that is just 2m prime plus 1 pi divided by n. Okay, when this numerator is 1, denominator is not. It is some small value. Okay, so we can even calculate what that value is. So when the numerator is 1, I over I naught is 1 divided by sine squared delta over 2, and delta we know what it is. It's this 2m prime plus 1 plus 1 pi over n. I substitute that here. So I get 2m prime plus 1 pi over 2n. And then because we can say for n large, this delta over 2 will be small. So I just replace sine squared delta over 2 by delta over 2, the whole square. And so that's just this, substituting this. So this allows us to calculate the intensity at the secondary maxima, approximately, without having to try and solve it, analytically or, numerically or something. And so we can ask, okay, so what is this for like m prime equal to 1? Well, we have I over I naught is 0.045 n squared. So it's n squared, but it's a very small fraction of that principal maximum. Remember, the principal maxima went as n squared I naught, but the secondary maxima go as 5%. This is for the first one, for m prime equal to 1. The other ones, m prime equal to 2, 3, etc., will be much smaller. In fact, we can even see how many there are going to be. This is also important to understand. Right? You can almost see that right here, right? Because we have delta over 2 is equal to pi and 2 pi. And in between, we have the minima, which is 2m prime pi over n. So you can see immediately that we can only have, say, 1, 2, 3, 4, right? 5. Okay. That's the total number of minima in between those two. And then in between those, we're going to have the maximum. So we get 1, 2, 3, 4 secondary maximum. Okay. And those will be even smaller than the principal maximum, as we just saw. Okay. Okay, so now I'm going to talk about any questions on this. Understanding the behavior of this n source situation is very important because we'll see it immediately allows us to also talk about the single slit and other cases. And this pattern of sine squared n delta over 2 by sine squared delta over 2 shows up in many other problems as well. Okay. if you don't have any questions, I want to talk about an application of this to phased array radar and very long baseline interferometry in radio telescopes. Okay, so the idea is that we know that the phase, sorry, this should have been delta, I written it as phase, phi. Okay, so that's the phase difference between any two points in the n source array. So ignoring the epsilon, this is just 2 pi d sine theta by lambda, where d is the spacing. Here now we are taking radios. So these are radar antennas. Okay. And these radar antennas, now, as I said, their spacing is d. So that's 2 pi d sine theta over lambda. Okay. And then in addition, it turns out because they're radio sources that are driving these antennas, I can add in a phase difference between the radio sources, because it's easier in the radio domain to control the phase of the electric field or the source that's driving each of these antennas. So I can make this an additional epsilon, which is tunable by the experimenter. And notice, remember, we already talked about this several times, but let's say the peak and then the addition. So like if I went here, one slide back, right here, you can see if suppose I had set delta equal to 2 pi, right? Delta over 2 equals 2 pi, delta over 2 equals pi, that means I'm fixing the angle at which I get this, the second, this principal maximum. Of course, delta over 2 equal to 0 will be right in front of the array, okay? But I can also tune it away from that by just changing to delta over 2 equals pi, okay? And now, that allows me to control the angle theta at which this principal maxima occurs. By altering epsilon, by tuning it, which I can do almost in a continuous fashion, I can scan theta where the secondary, say, one of the principal maxima occurs by just moving epsilon. Okay. So this is how phased array radars work. Turns out this principle is very powerful, not only in radio telescopes, it occurs again and again in like optical domain, it occurs in like many different situations. Okay, so this is a very important and nice principle. And so I hope it's clear now to you how to use these n source problems to like understand the behavior of many different phenomena. Okay. This is just that same sine function. I just drew it as I divided by n squared. I know here. So just I removed even the n. Anyway, so another application. So of course, I just told you about the phased array radar and how adding a phase change can change the direction of the maximum. You can also run this backward, meaning by the principle of reversibility, instead of having a source here and sending the beam out to scan the radar beam across the sky, right? You can reverse it and say, if I'm looking for signals from space, radio signals, right? Which there are many sources of radio signals in the universe, and these radio signals now can be, I can go across the entire sky by scanning, for example, this epsilon between the radio telescopes. Now, one way to do that is by scanning the phase of the local oscillator that sits in the radio telescope. There's just ways of like doing that, but of course that would require synchronizing between one radio telescope and another, right? That seems a little bit difficult because especially if the radio telescopes are located in opposite ends of the Earth, for example. So for very long baseline interferometry, they go an additional step further. They record the timing of the signals that they get from each of these. So let's say one radio telescope detects a peak signal, right? So they get some peak in the radio signal, okay? And then they record the time of that signal, and they can record the time at a different signal. And using that, they can extract the phase information from those signals. How exactly that's done, obviously that's a thing for another course, but this is the central idea, again, to use the phase difference between the radio fields from the timing information, and then thereby they extend the baseline of this radio telescope. So instead of just being restricted to a dish, that is the size of the central dish, which remember, we've already talked about this to some extent, that the size of the lens or the telescope, etc., controls the brightness of the signal. So that's one reason to have bigger and bigger telescopes or bigger diameters. But also, it turns out resolution is also affected by the size of the telescope. And we can see that it's on this slide, but you can see it by the fact that the central peak is I over n squared I naught, and then it falls off very quickly to the first minima. Remember the first minima where that came from. What was that value? First minima was n delta equals 2m prime pi. So the bigger the size of my array, the sharper that first peak will be. Does that make sense? Because the first minima occurs when delta equals 2 pi divided by n. So if n is very large, meaning effectively the size of my array is very large, now that central peak is going to fall off very sharply with the angle. So you get very sharp peaks, which improves your resolution greatly. Okay, so size of the telescope is inversely proportional to the resolution, meaning the larger the size, the sharper, smaller the features that you can determine, because your peak is now falling off very quickly with n, the size of the telescope. Okay, so this is very powerful, again, as I mentioned. And so that's how they set up radio telescopes to get very very good resolution in the universe, even though the wavelength of radio waves at first is like very large, so you might think you can't get very good resolution with that. But it turns out because you can generate these very large baseline radio interferometers, VLBI, right? Very large baseline EI interferometers, as they're called, you can actually get very sharp pictures. I think one of the most recent examples, has everyone seen the image of the black hole in M87A? Have you seen that? Like, it came out like a few years ago. So that was generated using data. They had I think there's a famous picture of that, one of the graduate students on that project with like this stack of like hard drives. And the stack of hard drives was filled with like radio telescope signals. Okay, and then they wrote, whatever code to reconcile all of that to like generate that image of that black hole. Okay. Okay, so I'm going to stop here as far as n source oscillators before I move on to the single slit case, which I want to complete today, because it's also the thing. Any questions about the n source and how we use it in different applications, like antennas, etc. A physical picture of the phasors, I ask you to like really take that to sort of, in your mind, because a lot of times, even if you can't directly derive the result from a function, by remembering those kind of physical pictures about what's going on for minima and maxima, you can easily figure out what the answer should be without having to derive the whole algebra of the sine squared functions and so on. Okay, so now we'll go to single slit diffraction. The idea of single slit diffraction is, well, we can see that there are many sources. If I were to approximate, along the y-axis, so the slit is along the y-axis, it has a length small l, which is very large, much larger than a wavelength. So we don't expect much diffraction along the y-axis, meaning we can think of the y-axis as essentially just geometric. Okay, because the wavelength is much smaller than the distance L. So we can think of this L, this entire strip over here is replaced by a single point source. The proof of that I will give you in a separate small supplementary lecture, because we can prove it from this n source oscillator argument that I've just shown you. But I'm just going to assume that effectively I can think of this as having. So I'm basically saying that each strip, well, I'll draw that, but is replaced by a little point source here. And then I can think of many strips, right, going along the y-axis. Each of them is replaced by a point source. So now I have n point sources, effectively infinite, but I'm thinking of it as an n source problem. Those n sources now, really the dimension that matters is this distance b. So when b now approaches lambda or is smaller than lambda, I'll get diffraction in the xz plane. Okay, the diffraction that occurs is in this XZ plane. And of course, this picture here is just the Fraunhofer diffraction circle. We don't want to worry about having to make the distance very large, so we just replace it by these two lenses. Okay. Any question about what I'm doing, the approximation? Okay, so now I just have to worry about this B direction. Okay, and so so replace by point source in the XZ plane. Yeah. Okay, and then I claim the formula which gives me the answer for the intensity pattern is this formula over here. It's sine beta divided by beta whole square, where beta is now kb over 2 sine theta. Okay, you may wonder how I got that. Well, we just go back to our n source problem, and now we're just going to approximate n going to infinity. Okay, where n is the number of sources. So the formula for n sources was sine squared I naught sine squared n delta over 2 divided by sine squared delta over 2. But remember, delta is basically 2 pi over lambda naught d sine theta. The d again, I'm just reminding you, was the spacing between any two sources. Okay, so I have n sources, they're all each separated by 7. Well, if I want to go to a source, which is a slit, so this is a slit, just going to, here is just metal, and then here in between is where the actual slit is open, right? And this has a dimension b. I'm replacing this, as I said, by a set of point sources. Okay, I'm imagining that there's a set of point sources in the slit. Okay, and there are n of them, and the total dimension of the source is b. Well, clearly, I can just set n going to infinity while d goes to 0, such that nd is equal to b. Right? If I make that approximation such that n times d remains fixed while n goes to infinity, which means d must go to 0, I can then find the expression, and that is just I naught sine squared. So this n delta over 2 sine theta. Basically, if I replace this 2 pi over lambda naught times n times d sine theta, that is in the numerator divided by 2, and I replace the sine squared over here, 2 pi over lambda naught d sine theta. Okay, as I said, when nd is going to this point b, I get 2 pi over lambda times b sine theta divided by 2. Okay, so if I call that as beta, then the denominator is just beta over n. So this whole thing is beta, or is it beta over 2? What do I call it? No, that is beta. So that's the one slight. I wish they had maintained consistency in your textbook. I'm following a textbook for this. So what they did here is, so far we've been calling delta as 2 pi over lambda naught d sine theta. But for this one thing, they went to beta equals essentially this n delta over 2. So basically n delta over 2. So that is basically pi over lambda b sine. So that's the one slight wrinkle that they threw in the textbook. So I want to follow your textbook. That's why I'm using the same expression. And then over here, so this is beta, then this must be equal to beta over n. Okay? And the square. Okay. Well, okay, there's a factor of n, and you might worry that that might go to infinity or something, but that's all going to be normalized away as just the intensity from the line source. So I'm still going to call that I naught, and I haven't proven this, but you can prove it as I'll do in my supplementary math video. So that's just essentially taking this process that I've outlined physically. I mean, I hand waved it basically into existence, but you can prove this by taking the integral formula. So instead of doing this as the sum of this going to infinity, n going to infinity, and d going to 0, I can break up the slit into small strips, do the integral, and I'll get the same answer that I just got. Okay, the last thing then I want to quickly go over is sorry. We have a couple minutes, and we also need to get to the quiz. So this is that function sine beta over beta, the whole square. So it looks very similar to the other one, except it doesn't have all those principal maxima over there. That's what you have to see. So there's only a central peak followed by a minimum and then some secondary minimum. And that's it. There are no additional principal maxima out here like we had in the n slit or n source case. And again, immediately it becomes obvious where the first minima must be, because the numerator goes to 0, but the denominator remains finite, right? That's where you get a 0. That's easy. Sine beta will go to 0 and beta equals pi. So we get a pi here and a minus pi, of course. So that effectively tells us the width of the central maxima right here. So that is just, I'm just writing that. So if I set beta equal to pi, what I get, and you can write that also in terms of sine theta. Remember, beta is just pi over lambda times sine theta, b sine theta. So that's beta. So if I set pi over lambda b sine theta, and I write this in terms of sine theta in the x-axis instead of beta, then I get sine theta has to be lambda over p. Again, remember going back to the first situation, I said sine theta whenever it's lambda over something that's relevant to the problem. In this case, the relevant dimension of the problem is the width of the slit. So whenever sine theta approaches some lambda over something, that kind of fits the width of the maximum always. This will be a common sort of pattern. Okay, so the total width from here to here is 2 times lambda over b, and 80% of the intensity is in this center of x. Effectively, almost all of the intensity is in here, but yes, we do have additional maxima, which you can easily work out for yourself by just finding where that sine beta or beta is maximum, basically, or in between. Again, you can see it, right? The first minima is pi, the next minima is 2 pi. The secondary maxima is at almost halfway between. It's at almost 1.5 pi. Same thing over here, and so on. So it's close to a good approximation. You can just set in between for the secondary maximum. And as I said, if you want to be more accurate, then you put it into mathematics. Okay. So the last thing, I guess, maybe I should come back to this. Okay, well, actually, it's pretty quick. So I've already shown you where the minima occur. For the maxima, well, okay, that's just setting di over d beta equal to 0, and that's just calculating using the chain rule what this function must be, and setting that numerator equal to 0 gives me tan beta equals beta. Okay, so tan beta equal to beta will be where the maxima occur, and to understand that, you can then plot tan beta, you can plot the function beta, or you can use Mathematica to give you the roots of the transcendental equation, and that will give you all the different places where this intersection point happens. And as you can see, it's very close to 3 pi over 2, but not quite. Almost 5 pi over 2, etc. Just like we talked about in the previous slide. Okay, I'm going to save this. This is the physical picture of diffraction from the single slit. I'll talk about this in the next class. But for today, let's just go quickly to our quiz. It's over here. Okay, very good. Okay, so this is our question for the day. Single slit diffraction pattern is observed with green light of 532 nanometers. Then the wavelength is doubled while also doubling the slit size. What will happen to the positions of the minima in the diffraction pattern? Will they remain